So to talk about energy with simple harmonic motion, let's actually concentrate on thinking about our spring and mass system. It's sort of the simplest one to kind of lay out the argument we're going to lay out here. So again, what do we do with spring and mass? Well, I'm going to pull the mass out to amplitude, and I'm going to let it go. And so it's going to start moving back towards equilibrium. When it gets to equilibrium, it'll be moving its fastest. It's going to continue to slide over until it gets to the opposite amplitude. It's going to come to a stop there, and then it's going to begin to bounce back so that, again, as it passes through equilibrium, it's passing at its maximum speed. Initially, when I pull the mass out and let it go at amplitude, all the energy of the system is in elastic potential energy. Right? At the instant I let it go, the mass isn't moving, zero kinetic energy, so all the energy of the system starts in elastic potential energy. As it comes back through equilibrium, however, all the energy of the system is now in kinetic energy. So when it's at equilibrium, there's no elastic potential energy acting on the mass. All the energy that started as elastic potential energy has now been converted into kinetic energy. And so fundamentally, that's what's going on in simple harmonic motion, is the energy of my simple harmonic oscillator is being transferred back and forth between kinetic energy and elastic potential energy. So it's entirely elastic potential energy when it's at the amplitudes. It's entirely kinetic energy when it's at equilibrium. Well, if I want to keep track of the entire energy at any point, I know that it's just the sum of those two. So the total mechanical energy of my spring and mass system is the kinetic energy plus the potential energy. So that's 1/2 mv squared plus 1/2 kx squared. Well, I can use my equations of motion here. And so I know that x is a cosine omega t plus phi, that v is negative omega a sine omega t plus phi. And so I can plug that in and calculate out that the total energy ends up being this big expression. It's 1/2 m omega squared a squared sine squared omega t plus phi plus 1/2 k a squared cosine squared omega t plus phi. And as I look at this, I see cosine squared and sine squared, and I know that when I add sine squared plus cosine squared, that gives me 1. And so it would be really nice if I can factor everything else out, and so I'm left with the ability to add sine squared plus cosine squared and make that term go away. But as I look at it in front right now, I see a 1/2, that's the same. I see an a squared, that's the same. But I've got m omega squared in front of the sine squared term, and I've just got k in front of cosine squared. But of course, omega squared is k over m for my spring and mass oscillator, so sure enough, m omega squared is just another way of saying k. So I do in fact have, I can rewrite this as 1/2 k a squared sine squared omega t plus phi, which means that I can then factor out the 1/2 k a squared. I'm left with sine squared plus cosine squared. Sure enough, that's 1. And so I get the total mechanical energy of my spring and mass system is 1/2 k a squared. So this tells me a couple things. One is it says that the total mechanical energy of an ideal simple harmonic oscillator doesn't depend on position. So it doesn't matter where the mass is as it's bouncing back and forth between those two amplitude points. Its energy is always the same. And so just to be clear, we're thinking about an ideal spring, so no energy losses due to the spring, and we're thinking about it bouncing back and forth on a frictionless horizontal surface. So that's what we mean when we talk about this as an ideal simple harmonic oscillator here. But its total mechanical energy doesn't depend on position. In fact, the total mechanical energy is simply fixed by two parameters. How stiff is the spring, that's given by K, and then how far do you pull it away from equilibrium before you let it go. So those two details by themselves determine what the total mechanical energy of the system is. The second thing I noticed from this equation is that I actually started with equations in my equation of motion that did depend on time, but that time dependence disappeared. So the total mechanical energy of my ideal simple harmonic oscillator also doesn't depend on time. So it doesn't depend on what the position is, it also doesn't depend on when. So how far after you've let this go, it also doesn't depend on that. So I can confirm this by plotting out what's going on with the energy. So here's a plot of the energy as a function of position, and you'll notice that there are three curves here. The blue curve is the potential energy. So initially, when it's at amplitude, right? So I pull it over to this amplitude point and let it go. All of the energy is in the elastic potential energy. Once I let it go, however, it starts moving back towards equilibrium. And as it moves back towards equilibrium, the elastic potential energy decreases, the kinetic energy increases, until as it gets back to the equilibrium point, now it's zero for the elastic potential energy, and all the energy is in the kinetic energy. As it moves through equilibrium onto the other side, again, the kinetic energy starts to decrease as energy is built up within the elastic potential energy. And when you get to the other amplitude, now all of it is in the elastic potential energy again, because the speed of the mass has dropped back to zero. So it's kinetic energy is zero. The green curve is showing the total energy. And again, the green curve never changes. Its value is constant because sure enough, the total energy of my system for an ideal simple harmonic oscillator doesn't depend on its position. Well, we said it also doesn't depend on time. So what happens if we plot this out in terms of time? We're at amplitude, so we start with all of the energy and potential. Here's where my object is coming through equilibrium, potential zero. Here's where it's at the other amplitude. So this is halfway through the cycle. It bounces back through equilibrium. It comes back to where it started. So what you see is for this blue curve, it basically makes a W to go all the way through a full cycle. The red curve, on the other hand, the kinetic energy, it starts at zero when you release the mass. All the energy is in kinetic energy as it comes through equilibrium. Again, it's back to zero as it reaches the other amplitude. It comes back through equilibrium, all the energy is in the kinetic energy again, and then it finally gets back where it started, where again it's come back to a stop. So you can see how, again, over time, the same thing's true, that the energy is converted back and forth between the elastic potential energy and the kinetic energy. But when you sum that up, that green curve, the total energy of my system, sure enough, is constant. Right? So as long as we have an ideal spring oscillating back and forth on a frictionless horizontal surface, it will do that forever because there's not any way for the energy to be lost, and so it always remains the same.